Yeah. Hello everyone. It's our pleasure today to have Antonio to share about his recent work. And this work is really interesting. It goes beyond the typical unital noise that we assume for PQC. And this time they show a lot of interesting results regarding non-unital noise, like for example, like how non-unital noise will lead to epsilon barren plateaus. Of course, Antonio will be the expert in this, and he'll be tell us more about it. Antonio, the floor is yours.
Okay, thank you so much. And yeah, that's our recent work, noise-induced shallow circuit and absence of barren plateau. And I am a PhD student at Freie University of Berlin in the group of Jens Eisert. And this is a joint work with these nice people like Armando from Sorbonne University and EPFL, Shumik from University of Chicago, Sumit and Jens from Freie University. Daniel is a professor at ENS de Lyon, and Hihui comes from MIT. Okay, let's start. Let's start with a quick spoiler of our results and what we'll see in few slides in more detail and precisely. We will see that if we pick a quantum circuit of a fixed depth with realistic noise that I will define in a bit, what this means, only the last log n layers, where n is the number of qubits, matter for the task of estimating Pauli expectation values. And this happens with high probability, and we'll see precisely this statement in a moment. And this implies, since the last log n layer matter, lack of barren plateau for local cost functions, and leveraging the notion of effective shallow circuit, effective log-that circuit, we will show also how to efficient estimate Pauli expectation value classically. Okay, then let's start. The outline of my talk is about first introducing the role of noise in quantum circuit and quickly review previous results on the topic. Then explain our results on barren plateau, and then the notion of effective shallow circuits and that only the last log n layers can matter. And lastly, I will talk about the classical simulation of estimating Pauli expectation values. Okay. Understanding the noise impact in a noisy quantum device is very important for harnessing their capabilities and limitation. In fact, if we want to design quantum algorithm for these near-term quantum computers, taking into account noise is crucial. And that's not only for these years. Probably we will need to take into account noise for many more years if when designing algorithms for this device where fault-tolerant quantum computation is not yet fully available. And yeah, so this is very important also for theoreticians that wants to develop algorithms. And so we need to model the noise in our algorithm. And many previous works model the noise as solely depolarizing. And depolarizing noise is a kind of noise that with some probability, given in input a state, gives you the maximic state, and with the complementary probability gives you the initial state. So it pushes you more and more toward the maximic state. And yeah, it was shown that the polarizing noise is very detrimental for your quantum computation. For example, it was shown that the polarizing noise induces barren plateau in variational quantum algorithm that I will define in a bit, the notion of barren plateau, and also renders the supremacy sampling experiments, for example, the one conducted by Google, efficiently classical to simulate. For example, there was this talk at QIP 2022, where it was shown that if the noise in your circuit is solely depolarizing, then the advantage that you can have with potentially with supremacy sampling experiments will be lost. In fact, they have a polynomial time algorithm for this kind of depolarizing noise random circuit. However, if we perturb a bit our noise model from depolarizing to something a bit different, we could have different conclusions. For example, it was shown in this paper, Quantum Refrigerator, from Ben Hoare et al., that the nature of the noise matters a lot for quantum error correction purpose. If the noise is depolarizing, you can do certain stuff. If the noise is of another nature, like amplitude damping, you could do something different and better. Also, it was shown recently from Pfefferman and other nice people, and also my co-author Shomik Ghosh is here in this paper. It was shown that the assumption on which this Aranov algorithm for random quantum circuit sampling does not apply anymore if the noise is non-unital, where I will introduce the notion of non-unitality in a moment. And in particular, depolarizing noise is a kind of non-unital noise. So this assumption of this algorithm do not apply anymore. And also the hardness proof in this paper, strikingly, it was shown that also the hardness proof of random circuit sampling do not apply if the noise is non-unital. Okay, so both easiness and hardness of random quantum circuit sampling is open, up to date, with non-unital noise. And okay, however, real hardware noise is not solely depolarizing, which is a kind of unital noise. And the definition of unital noise is that the noise channel keeps the maximic state fixed. It sends the maximic state to the maximic state. And other noise components present in a quantum device are non-unitals, like T1 error, amplitude damping. And yeah, that means that if we give input the identity, we will have a linear combination of not only the identity, but also their Pauli. And yeah, if the depolarizing assumption, if true, enormously constrains noisy computation. And we will see what this means now, precisely. Let's consider a quantum circuit of a depth L. And we assume that the noise is depolarizing. The red dots here are the symbols that indicate depolarizing noise. And we assume that we have 2 qubit gates layer followed by depolarizing noise, and we have depth L. If the depth is larger than log n, where n is the number of qubits, no matter which gate you use, like any state at the output of this circuit will converge exponentially fast to the maximic state. That means that at linear depth, any circuit, any state output by a noisy depolarizing circuit is is statistically indistinguishable in Pauli time from the maximic state. And it's very straightforward to simulate a linear depth depolarizing noisy quantum circuit with any gate. You just need to sample from the uniform probability distribution, that is the one from of the maximic state. And yes, so this means that already at depth slightly larger than log n, in any quantum computation, any efficient quantum computation can be simulated with just sampling from the maximic state. And this implies that quantum computation, useful quantum computation, is possible only for log n depth. And in particular, for Pauli expectation values, this implies that any expectation value converge exponentially quickly to 0. So if you want to simulate, if you want to estimate Pauli expectation value with constant accuracy and inverse polynomial precision, at linear depth circuit of depolarizing noise, it's suffice to output 0. And for any Pauli expectation value. And Pauli expectation value is the focus of our work. However, all this that I've said here is not true if the noise is non-unital. Also, it's not true if the noise is a bit different from depolarizing. I mean, depolarizing is a kind of noise that is unital, but there are also other kind of noise that are unital, which do not satisfy these equations that I wrote here. For example, dephasing noise is a kind of noise that is unital, but do not satisfy this. And in our work, we will address both non-unital noise and also this more general kind of unital noise. Yeah. By the way, if you have any questions at some point, yeah, I'm free to take. I don't know the policy of your seminars. How is it if you want question at the end? But I'm happy to let you interrupt me at any point. Okay.
Yeah, sure.
Okay. So, like we've seen the behavior under depolarizing noise for Pauli expectation values. And Pauli expectation values are very important for example, variational quantum algorithms. And let's talk a bit about that. Okay. I will focus here on introduction barren plateau. That is a problem for variational quantum algorithms. And variational quantum algorithms are kind of algorithms that encodes the problem into finding the minimum of a cost function. I mean, the problem is encoded in finding the minimum of the cost function. And the parameters of this cost function usually are taken like the parameters of the gate of the quantum circuit. And phi is here is my quantum circuit, and U1, UM are the parameter indicates these gates. And barren plateau, informally, is that phenomena that you have when, for most choices of the parameters gate, you find yourself in a point of the landscape that is flat, and means that the gradient norm is very, very small. And we will see in a moment precisely what does it mean. And okay, that's an example of the landscape with barren plateau. I was here during July 2023 during a summer school, like was Salt Lake and in Utah. And for example, a landscape with barren plateau is like this. You have, if you sample or read randomly parameters, you could find in this flat landscape. And yeah, moving here, for example, using gradient descent could be challenging to find, for example, the maximum point. And yes, so let's go back to this circuit framework. And in variational quantum algorithm, cost functions are usually made by Pauli expectation values and using these kind of objects. And the Pauli expectation value are estimated through samples from your quantum circuit. And also, if you are in a flat region, in order to distinguish two different Pauli expectation values, since they are very close, you need to take really lots of sample to appreciate this difference. And one other question that one can ask is how much variation in the gate mu affect the cost function C? And the relevant quantity here is the partial derivative of the cost function with respect to the parameter of the gate mu. And if the variance over the probability distribution of the parameters of the random circuit of this partial derivative is exponentially small, then this influence is very unlikely. And this in the literature is also said that the gate is not trainable. Also, I mean, one can read this equation through Chebyshev inequality, for example, and since the variance is exponentially small, this means that the probability of having finding the partial derivative larger than any constant is exponentially small, or also the partial derivative larger than any inverse polynomial in the number of qubits quantity is exponentially small. And yeah, so, and that another reading of the variance is that where like it's the oscillation around your mean, the deviation around the mean, and yeah, the mean of the partial derivative is 0. So you have partial derivative that are it's exponentially unlikely to find a partial derivative value that is outside 0, if that's true, like very far from 0. Okay, and so let me review previous result on barren plateau. It was shown that if we don't have noise, any kind of noise in the circuit, at linear depth, we have barren plateau, and that means that the variance of the cost function is exponentially small. It means that the cost for most of the region of your parameter space, like the value of the cost function is very, very close to 0 for in this case. And like here, like this result should be also not so surprising for those of you that are familiar with random circuits and true design. It is known that linear depth random quantum circuit, like where these 2-qubit gates are sampled from, for example, the uniform distribution over the 2-qubit gates, they converge to a so-called true design, and quantities like these are like that are second moment quantities are exponentially small in the number of qubits. Yeah, that's was just a comment. And in particular for the partial derivative, it was shown also that any partial derivative in the circuit is exponentially small, and so any gate has very little influence on on the cost function for most of the parameters. Okay, and all the gates are not trainable. In the depolarizing noise scenario, it was shown the same of before, same of the noiseless case. And this also should not be too surprising because of what we saw before, that any circuit with the depolarizing noise converge exponentially quickly with the depth. And okay, now let's see non-unital noise. That is.
Can I ask a question?
Yes, sure.
So all these results are for random circuits, right?
Yes.
But they are not really relevant for variational quantum algorithm, no? I mean, there you choose a circuit which is particular. You're not interested in the random circuit. You're choosing your circuit.
Yeah, I mean, okay. Here the random circuit is defined like you have any fixed depth, and you associate to each 2-qubit gates a probability distribution. Barren plateau is a phenomenon that happens when you initialize your circuit, and a natural choice that one could do is or also easy for analytical calculation is to randomly choose these 2-qubit gates randomly from the uniform distribution over the 2-qubit gates. And yeah, through your computation, it's yeah, you don't have a true like if you have already a good region of the landscape, it's true you don't have a random circuit. But in the moment that you have to initialize your quantum circuit, if you don't have any knowledge how to cleverly initialize, I mean, this result says that for most of the choice of these gates, where most of is defined with respect
so
to
it's for the initial point that it is hopeless.
Yes.
But
the initial point
you can grow your circuit,
iteratively.
From something very shallow to something.
Exactly. I mean, this is just for initialization in the absence of knowledge of how to cleverly initialize your circuit, but I mean, crucially for noiseless. For depolarizing noise, we have seen before that any circuit at linear depth or at depth larger than log n is basically indistinguishable from the maximum state. So you can simulate anything with depolarizing noise with just uniforms, like sampling from the uniform. So I mean, in the noiseless case, yes, totally true. If you have better initialization, then use initialize randomly your parameters. And here in these theoretical results, randomly means exactly from the uniform distribution over the 2 qubit gates. Then, I mean, if you don't have anything, like if you have other strategy, you could, these results do not apply.
Okay, thank you.
But thanks for the question. It was very important, I think, to verify this. Okay. However, like, let's see what happens with non-unital noise that is the subject of our work. And in the same framework where we assume that the 2 qubit gates are sampled randomly from the uniform distribution over the 2 qubit gates, we show that we have no barren plateau at any depth for local cost function that we'll see in a bit. What does it mean, local cost function? And precisely this means that the variance of the cost is omega 1 is a constant. And that means that the oscillations, the deviation from the mean, if you randomly sample your circuit, the deviation you can be, it is likely to find a point that is far from your mean. So you don't have an exponential concentration like in this case. And but we also show that the importance of each gate decreases exponentially from the end. I mean, the variance of the partial derivative decrease with the distance from the end. And so we have this picture that the partial derivative until log n are inverse-polynomially small, so we could still appreciate this kind of variance of partial derivative, like estimate with Pauli sample and so forth. Like while if we have here, we still have gates that are non-trainable. So we have that only the last log n layers matter. And in a moment, we'll see different readings of this claim. It's not only about barren plateau. Okay. And also another work recently came out on arXiv where it addresses like a similar question with a slightly different noise model. So check it out. And okay. Let's go a bit deeper into these results about the barren plateau. Our first result is that for any Hermitian operator, any depth and any initial state rho, 0, if we like take like I mean the variance over our circuit of this expectation value is this, and the crucial thing here is that each Pauli component is exponentially suppressed with the Pauli weight, where the Pauli weight is the number of non-identity terms in your Pauli string. Like, for example, Z has Pauli weight 1, because there is only Z that is non-identity. Okay, from this, it follows that local cost functions do not suffer from exponential concentration. For example, Z1. Local cost functions, here I define like cost function associated to a local Pauli, where local Pauli is a Pauli with Pauli weight 0.1, for example. And another corollary of this result is that global cost functions suffer from exponential concentration. And an example of a global cost function is Z tensor n, because I mean, it's the Pauli weight is order n. And the variance is exponentially small in the number of qubits. That means that if you take randomly the parameters of your circuit with high probability, you will find yourself close to the mean that is 0. Okay, now let's go a bit deeper into partial derivative result that we mentioned before. We show that at any depth, also geometrically locality is not really important. Here it's a 1D circuit. And any Pauli and any noise. Here I'm not assuming anything on the noise apart that is acts locally. We have that the partial derivative is exponentially suppressed with the distance from the end of the gate and also with the Pauli weight. Also, we show that if P is local, it means like, as I said before, like Z1 or XX, I mean, something that where the non-identity Pauli is just order 1 in number of qubits. Then for any non-unital noise, we have we have a matching lower bound for this equation, for this upper bound, and that means that these gates are trainable in the last log n layers. And as a corollary, we have that the expected value of the gradient norm square is also a constant. That means that the probability of finding a gradient norm that is not exponentially concentrated is very, very large. So, I mean, we have a large, it's very likely to find a probability space, to find a point in the parameter space that is where the gradient norm is very large. And okay, of course, these parameters depends by the non-unital noise. I mean, if we don't have a non-unital noise, this result is non-true. So, I mean, this omega is hiding parameters of the non-unitality. And okay, if P is global, like X tensor n, then any gate becomes non-trainable. And yeah, the last log n are not anymore trainable. And okay, for the particular case of unital noise, our result reduced to the unital to the previous known scenario. And like in particular, the variance of the partial derivative is not more exponentially suppressed with k, but with all L, any partial derivative. And this also improves a bit over the previous result for the particular case of unital noise, because taking account other noise like dephasing that are unital and also are of a different nature of the polarizing noise. The polarizing noise is of a special family because if you keep supplying multiple times, it converge. You're sure that converge to the maximic state. While other kind of unital noise like dephasing, this is not really the case. Okay, and now let's go to.
Sorry, I have a question over here. Yeah. So okay. So this could be a naive question, but over here you consider the case where every noise is non-unital and the other one is that every noise is unital, right? So what if you have a mix of unital and unital or non-unital, and how will that affect the trainability of the circuit?
I mean, our results apply for any noise.
Yeah.
Also, and in particular, if you have depolarizing and also a tiny deviation for depolarizing, like you can think depolarizing followed by amplitude damping, where amplitude damping is something that basically resets you with some probability to 0. You can think like this. Then our results still apply. So very small deviation from depolarizing noise implies our results. So yeah, I mean, and so you can have unital and non-unital. In particular, unital and non-unital is still non-unital. I mean, because if you input so even very small deviation from the unitality, like composition of two channel, like depolarizing and amplitude damping with very small amplitude damping, still gives our result.
Right.
But yeah,
so,
I mean, it's a very.
So it's like the non-unital noise will kind of dominate over the unital noise. Can I understand like this?
Yes, exactly. Even,
Okay.
I mean, there is no threshold. I mean, for any value of larger than 0 of non-unital noise parameter that is, I mean, before I said that the identity channel that maps identity to identity is unital, but in general, a single qubit noise channel can map identity to a linear combination of Pauli, of single qubit Pauli. If any of the parameter, if one of any parameter of this x, y, and z is, is larger than 0, then we have our result. Okay.
I see.
And in particular, okay, single qubit noise channel are not, expected to depend by the parameters are not expected to depend by n, by the number of qubits. But yeah, if you want really a threshold, if the noise parameter is exponentially small in the number of qubits, like the non-unital noise parameter, then our results do not apply anymore. But if even like for inverse polynomially, you have a similar picture to our results. So
right.
But for any cost value, like it's really how I described here also.
Right, but in any case, like the inverse polynomial noise is what we expect in a typical hardware, right? So I guess this should be fine. Okay. Yep. Thanks.
You're welcome. So let me go deeper in these effective shallow circuits. And okay, we show that any Pauli expectation value is, if you take your Pauli expectation value and it's suffice to take just the last k layers to have an exponential in k precise estimate of your Pauli expectation value. In particular, like here it's the circuit where, for last k layers, this chunk of the circuit, truncating your circuit to the last k layer and computing this over your initial state suffice to have an exponentially precise in k estimate of the Pauli expectation value. And this follows from the more general theorem that is this. For any rho and sigma, any also whatever quantum state, possibly mixed, possibly exponentially complex, the average over a quantum circuit of depth k is exponentially suppressed on k. And this follows by substitution here that I will not go into detail, and also using the fact that the probability distribution of this chunk of the circuit and this chunk is disjoint. And okay, all these results that I'm showing can be strengthened like with the Pauli weight. You have also an exponential suppression in the Pauli weight okay. Using this result,
sorry, what noise assumption here?
Here we really don't have any noise assumption. These results holds for any noise that is not unitary. Like any noise that is not a unitary channel apply. Is not assuming non-unital noise. We have seen that for unital noise, like for depolarizing noise, we can strengthen. In the first slides we've seen for depolarizing noise, we can show really worst case in any circuit convert to a maximic state. So yeah, but here, assuming really general noise, we can give this.
So the noise is not unitary. That's the only thing.
Yes. The noise is not unitary. Yes, that's
okay.
the only thing. For this upper bound. For the lower bound that I showed before, like the last log and layers matter, the partiality is Ig, then I assumed non-unital. But it's a very good point. These results holds in general for any noise, in particular also for other kind of noise that are unital, like dephasing, that is a different nature of depolarizing. Okay,
thanks.
And you're welcome. Okay, and then this result, this theorem, like sounds already from a bit like indistinguishability between phi rho and phi sigma. In fact, we using this theorem, we can show this thing that the trace distance I mean, the average one norm between phi rho and phi sigma is exponentially small in the depth of phi, where here L is larger than omega n. Yes, so this statement says that basically, if on average over the choice of your quantum circuit, if you apply both to rho and both to sigma, I mean, the output is statistically indistinguishable with high probability. And yeah, at linear depth, crucially. And yes. However, I mean, one can be a bit confused. I mean, can say, okay, but why you are showing this result with expected value? Is it possible to show these results in general, like any noisy quantum circuit will have this property? However, the answer to this is not. Like, there are easy example, like there are easy example like with the dephasing noise that also is unital. I mean, where this kind of inequality does not hold in general without expected value. And also more strikingly is in this paper by Gottsman, Benor et al. It was shown also how to leverage non-unital noise like amplitude dampings to perform long fault-tolerant quantum computation without fresh ancilla. It means that the trace distance, the trace norm between phi rho and phi sigma, if you engineer well your quantum circuit, you can compute for like a very long depth, like exponential. Also, you can do fault-tolerant quantum computation for exponential depth. And so the trace distance cannot be exponentially small in the worst case. Here it's an average case statement, okay? And yes, so however, like this theorem that was shown in this paper assumed a threshold, and that refutes that our theorem can be applied without average. But however, in the eigennoise regime, if the noise is quite high, we can obtain this result in the worst case. And here in particular, if the depth is larger than log n, and we assume informally very noisy circuits, then yeah, we have this exponential convergence. And yeah, the trace norm is a meaningful notion of distance between quantum states because it's related to their distinguishability from the Olivo-Elstrom theorem. But yeah. Okay, then let me go into the classical simulation of Pauli expectation value. And now I will show that how to simulate Pauli expectation value of most of noisy quantum circuit. We saw before that estimating Pauli expectation value under the polarity noise, if the circuit is deep enough, is very easy. You just output 0. Now, and you will be precise with exponentially small error if the circuit is linear depth, for example. Now let's see in general for any noise. Okay, so the solution is, and we will show in a bit why it's the case. It suffices to output just what you have. You truncate your circuit to the last k layer with k picked. I mean, with precision according to the precision that you want to estimate, and you just compute this quantity for rho 0 that, for example, is 0 tensor n, and this suffices. Just truncate your circuit to compute your Pauli expectation value. Now we'll see why this can be done efficiently for constant or inverse polynomial precision. Okay, the previous presupposition says that if we take rho 0, 0 n, 0 n for any Pauli p, we have this. That the error of this truncation, if we truncate this circuit, the error that we introduce is exponentially suppressed in K and also in the Pauli weight P. But let's focus here on local Pauli, like P that is order 1. So we have exponentially suppression in K. And so choosing a k that is order of log epsilon minus 1 suffices to have this error smaller than epsilon. We can pick k according to our wanted precision. And so our output is this. Let's see why we can compute it efficiently. I mean, this follows from so-called light-cone arguments that now I will introduce in a bit. Like we have our expectation value here, and we take the adjoint of this channel on the observable, Pauli. Now, if P is local, is just Z1, for example, and this phi is a quantum circuit that is geometrically local, I mean, it's just few layers, like k layers, and k is not, it's a constant, for example, then also this will be local. And this, also this observable can be local. And I will now expand a bit on this point. This is the so-called standard light cone argument that if you didn't see before, it's worth to see this image at least once. Like here, I'm considering just the last k layers of the circuit. I mean, here it's my, for example, if this is noiseless, I have my unitary U, and this is a U dagger, and this is my observable, my Pauli. And I'm considering just the last k layers. And anything, if I have a local Pauli, a geometrically local circuit, I mean, this gate here do not matter because they trivially contract for U dagger. I mean, so if there is no Pauli acting here, then these gates are really U dagger equal identity, so they do not matter. I mean, so in the noiseless case, this gate do not matter, but also in the noisy case, one can generalize it and see the same. And so the quantum computation involves only k qubits, order k qubits. If this is depth k, the number of qubits in this light cone that I have to consider for my estimation is only order k. Rho 0 crucially is a product state. So yeah, also 0, 10, I mean, this rho 0, 0n, 0n here, since this is local, becomes 0k, 0k, only on k qubits. So this can be computed efficiently for this kind of light cone arguments. And the computational time is exponential in k, where k is log epsilon minus 1 because of this. So the computational time is polynomial in epsilon minus 1. And so for any constant precision and any or inverse polynomial precision, for most of choices of this quantum circuit, we can estimate accurately our Pauli expectation value. Okay, some of you might be concerned about this notion of most, like it is an average notion simulation. Okay, for this, we also give, a slightly more favorable things to check if my noisy circuit is classically simulable. That is, we give a verification condition. Given a noisy circuit, we want to say if this is one of these most circuits where we can simulate our Pauli expectation value or not. And the verification condition that I will not expand much here is just check if this quantity here is proportional to the identity. Since we have just k qubits, order k qubits, this condition can be efficiently verified. And this is a sufficient condition to say, yes, our estimation will be accurate. And however, it's an open question to have like some high probability of this event happen. And yeah. So in summary, we have shown that there is a classical algorithm to estimate local Pauli expectation value to epsilon additive precision on average over the class of noisy quantum circuit of any depth. And the runtime is exponential log d epsilon minus 2, where d is the spatial dimension of the system. Before I showed 1D, but the same arguments can be applied to arbitrary dimension. And this implies that for constant precision, the algorithm is efficient for any dimensionality, like 1D, 2D circuits, or whatever. Like, but for Pauli inverse polynomial precision in the number of qubits, the algorithm is efficient for 1D architectures, and the quasi-polynomial for d larger than 1, like d equal 2. And okay, here I assumed local Pauli to apply Lightcone arguments. However, if the Pauli is global, like x tensor n, there is no need to run any algorithm to simulate this kind of noisy circuit, since we have shown that most of these circuits have will be likely to have Pauli expectation value of global Pauli exponentially suppressed in the Pauli weight. And so output 0 succeed with high probability if the Pauli is global. And so this is an algorithm for estimating Pauli expectation value or arbitrary dip, possibly non-unital noisy random quantum circuits. It's not an algorithm to estimate the Pauli expectation value of any fixed circuit. Also, we've seen before that one can do fault-tolerant quantum computation if one engineer precisely the circuit, so we cannot expect to find a classical algorithm that simulate worst case, not random noisy quantum circuit with general noise like non-unital noise. Okay, so yeah, we introduced this average notion to avoid this problem. And okay, the proof ingredients, let me just briefly mention, are using the two design properties of the two qubit gates, and also work in the so-called Heisenberg picture, that is just take the noise on the observable and just work on the observable. We have seen that the last layer matters, so usually just taking the adjoint of the few last layers suffice to reach the result. So working in the Heisenberg picture simplifies lots of the computation. And also we exploited the nice convenient form of noisy channels. I mean, since we have these two qubit gates that are sampled uniformly, we can use the unitary invariance to parameterize any single qubit channel by like this. I mean, we have some kind of sparse channel. I mean, we have any general channel, but any general channel, if we have some this notion of unitary invariance, can be brought to this form, where we have just these parameters here, and in general, we have more parameters for any channel. But I mean, this is like sparse Pauli transfer matrix that parameterizes the single qubit noise channel. And yeah, if Tx, Ty, Tz, these are larger than constant, then we have absence barren plateau, and this kind of stuff. These are what I mean non-unital noise parameter, the one that are here, parameterized by T. Okay. So let me quickly go through the numerical experience, and then I will conclude. Like we assume that the parameters are sampled by, I mean, the gate are sampled by the uniform distribution, or also a bit weaker notion, we assume just the distribution to be a true design over the two qubit gates. And but however, in our numerics, we also saw that our results hold for more restricted class of circuits, like this kind of more symmetric circuits, like QAOA type circuits, that where the two qubit gates are not like true uniform over the distribution of the two qubit gates. And our results are confirm what we saw before with this less strict assumption, and this is the variance of the partial derivative with respect to the last layer, and we see that the polarizing versus amplitude damping, it's a constant value, achieve a constant value, while with the polarizing noise we have exponentially small partial derivative with respect to the last layer. And if L is the depth from the end, we see that if we take the partial derivative with respect to a gate that is L layer from the end, we have this, for amplitude damping and depolarizing, we have this exponential decrease of importance, while for only depolarizing, we have always very small variance, no matter where the parameters partial derivative is taken. Okay, so the conclusion is that any amount of non-unital noise induces absence of barren plateau, but it truncates most quantum circuits to effectively logarithmic depth, allowing efficient classical simulation in estimating Pauli expectation values for these circuits with effective logarithmic depth. And yeah, the efficient classical simulation is really given by this effective shallow depth and leveraging late-con arguments. Okay, another conclusion is that assuming overly simplistic noise model could be misleading. We have seen that, yeah, like for example, barren plateau phenomenon is a bit different if we it's different if we have depolarizing noise, for example. And so assuming other little perturbation from this model, the picture change. And yeah, and another, I mean, taken together, our result shows that, I mean, also, since the last log n layers matter, any circuit, I mean, if you take, it's probably fair to take circuit of log n depth, where each gate is trainable, I mean, or at least to start with this. And that's the same of like noiseless shallow circuits. For example, noiseless shallow circuits, they do not have barren plateau like for local cost function. And yes, so I mean, we recover exactly what we have for shallow circuits that also for this reason our title is noise-induced shallow circuits, because like shallow circuits do not have barren plateau and have similar properties of what we show for arbitrary deep non-unital noise, possibly non-unital noise circuits. Okay, and the open question is, I mean, is to understand the complexity of classical simulation or random quantum circuit sampling with non-unital noise. And in this stock paper presented also at QAP, it was shown how to do sampling from random circuit with depolarizing noise. And in our paper, we show that arbitrary deep non-unital noise random circuit, you can efficiently classical simulate the Pauli expectation value estimation. However, a stronger notion of simulation is the sampling. And that's still an interesting open question. Okay, and thank you so much for your attention, and I'm happy to receive any of your questions.
Yeah, thanks, Antonio, for the very detailed talk. One specific thing that I want to point out is about the pictures of barren plateaus. Finally, like someone that I know, like didn't show the picture of desert for barren plateaus, and that this time instead you show like the salt line. Yeah, because typically people will show that. No, it's just the comments of the pictures that you put for barren plateaus, because like previously people keep putting like the picture of a desert, right, as a barren plateaus, and this time you put it as a salt lag, so it's a bit different. But in any case, so for the audience, if you have any question, feel free to unmute yourself or just type your question on comment, and then I could help kind of ask a question. Itai, you have a question to ask?
Yeah. So what if I consider this class of circuits that have non-unital noise? They are in some sense random, because I'm picking like a very shallow circuit, which is random with noise, but then I repeat it. So I'm in some sense looking at the fixed point of a quantum channel. Would your result hold for this type of for this class of circuits?
Sorry, you mean having the same circuit? I mean the same.
Yeah, I have like, I don't know, like 5, 6, 10 or log n layers. Maybe they be a random circuits, and then I repeat it.
Yes, with the same. I mean, with the same gates. With the.
Yeah.
You mean our model is this, and it's not the same. You mean because I mean, you say that this parameter here. I mean,
yeah,
these gates here are the same of these gates here, or what? I mean, yes. I mean, these results. I mean, the proof. It's a good question. I mean, our result really if okay,
because there was
okay,
also
probably
this paper from
join
2009, I think, or something like that, by Sirac. I think it was started also, and a bunch of other people. They showed about engineering dissipative quantum circuits, and that you can always like reach a fixed point, and it is like BQP hard, and so. So my intuition is that your result will not hold for that, for the same reason that this fault tolerance fridge kind of precludes.
Yeah, I mean, it's an interesting question. Like, I mean, now that I think, I mean, to prove this statement that you can truncate your circuit, you have an exponentially in depth of the truncation precise estimate. These assume independence of this chunk of circuit by this chunk. And I mean, you have this joint probability distribution. If you, I mean, correlate the parameter, if you have some kind, I don't know, also feedback or repetition parameters, our theorems do not
because
like
I think
apply.
if you repeat the same circuit, you can drive it to non-trivial points, maybe, or something like that.
Yeah, it's a very interesting point. I mean, I mean, in our analysis, okay, probably I don't know if they probably can be also tweaked to have some kind of, to take into account some kind of correlation of parameters. But they hold for, I mean, we assumed in our proofs that these gates are independently from each other. So this chunk of the circuit is independent from this chunk. The probability distribution of this chunk, yeah. So I mean, our result can be, I mean, our no-go, I mean, the effective log that can be avoided if you introduce some kind, probably some kind of correlation. I mean, let me give just 1 second of intuition why this effective log that picture happens. I mean, it substantially happens because you forget information. I mean, if you have noise, what at the beginning of your circuit, you just start to forget what you have at the beginning. Okay, so it's quite intuitive that yeah, like if you have at the end of the circuit what happened at the first gate, if you have layers, will be forgotten. So I mean, yeah, and so also if you think of, if you want intuition about absence of barren plateau and why these last log n layers matter, is because, for example, if you think about the probabilistic reset, like amplitude damping, that with some probability you reset your qubits, if you both these qubits are resetted, then if you have a Pauli here, I mean, it's yeah, these two qubit gates will matter a lot. Will be just a 2 qubit gates, 2 qubit. So I mean, with this, I mean, this is the intuition of our results. I mean, yes, but it's a very interesting point, the one that you brought, and yeah, in these things of the refrigerator that I mentioned, like the. Yeah, I mentioned the quantum refrigerator here.
Yeah.
And basically, the intuition why basically they show that if you have non-unital noise, for example, amplitude damping, you can do exponentially long circuits that, I mean, keeps the information, I mean, they are fault tolerant. And they are basically based on the fact that using non-unital noise, you can distill fresh unseal.
Right.
I mean,
you can cool it down to 0.
Exactly.
All right. Okay, thanks.
Yeah, you are welcome, and thank you for the very interesting question. I think, yeah, that's if we want maybe to avoid, okay, in this result, it's very important to introduce feedback or correlation between our circuits. And yeah.
Right. Any other questions from the audience? Yeah, maybe I could ask one. Like, it seems like it appears to me that this non-unital noise basically just like drive you toward the fixed points, right? Just like you guys have discussed and mentioned in your paper as well. And then I know like there's another line of research basically studying a so-called measurement induced phase transitions. Basically, you have a random circuit, and then you apply the measurement with some probability at each of the point after the you apply the circuit, right? And then the overall behaviors of the output stage will just change depends on your measurement rate. If your measurement rate is low, basically the overall state output state of your circuit will follow like volume law of entanglement. But then if your measurement rate is too high, then it will follow the area law of entanglement. Over here, I'm just wondering whether this will happen because like since like you are having the same kind of setting, you have random unitary, and then intermediate you are kind of performing some effective measurement, I would say, but then it goes to some other point instead of like in computational basis. Yeah. So yeah.
I mean, okay, it's interesting question. Okay, first of all, yeah, I want to point out the fact that I mean, the fact that we don't have barren plateau, it means basically that we don't reach a fixed point. This noisy state. I mean, if you pick a circuit, the distance of the circuit will matter a lot on for the output state. Like for the if you have the polarizing noise, you can be very sure to have the maximum state at the end. Here, since we have seen that we can reach large variances of cost function. I mean, these last layers matter a lot, so we don't have we have a different state if we change these last layers. So we don't have a really fixed point convergence here. But I mean, related to your point about measurement-induced phase transition, I think that that's very related indeed, and yeah, I would expect that. I mean, yeah, according to these results, I mean, our results also okay. We're not at all familiar very much with the literature of measurement-induced phase transition. Maybe I should be because it seems yeah, it's true that it seems very related. But what I can say is that our results also for this probabilistic reset that with some probability you reset your qubits, and that seems the model of measurement-induced phase transition. And our results show that yeah, you don't have yeah, I mean I don't know, like entanglement. Probably they look at entanglement, right? I mean,
Yes.
we show that there probably there is a transition. I mean, probably I don't know if they look Reni-2 entropy or maybe von Neumann entropy, but I mean, what I'm saying is that yeah, this model of probabilistic resetting a qubit is within our model, and we show that there is no phase transition. I mean, really for any constant value of the noise, we have omega 1 here, like these variants for the cost function. I would assume that if you change your observation and you don't look to this cost function, but for example to entropy or these kind of things, you would. I mean, if I'm not familiar with this measurement-induced phase transition literature, but yeah, I would expect that yeah, like since there, I mean what it's called the phase transition, you should have a phase transition that with for some low noise parameter you will have like something like that you have for maybe random states or large value of probabilistic reset, you don't have it. And yeah, but that's like, I mean, that's a different quantity by Pauli expectation values. So I cannot really say, apart from the fact that it seems very related. And yeah, like I think that probably the tools that we have used here could be used to tackle also this kind of question analytically. Like I don't know if I'm not very familiar with other work that tackled in this setting that question. And also in our paper, we address purity that is related to Reni-2 entropy, or also this kind of kernels methods. But I mean, there we have also similar results, but the picture there is a bit not so complete. So, I mean, we have a certain assumption on the noise parameters. That's why I didn't talk too much here. But yeah, check that. I mean, also in the paper, we have comments about Reni-2. I mean, this purity is related to entropy. So probably these results could be at least a bit useful, maybe. I don't know.
Right. Yeah. Okay. Yeah. Thanks for the explanations. Yeah. Maybe like after seeing your work and then people who knows the measurement in phase transition will just go and trying to study those kind of transition in a system. Yeah. Who knows? Yeah. Okay. So I think that we have running out of time. Yeah. We thanks Antonio again for the very interesting talk. And
Sorry,
yeah.
may I ask a final question? Maybe also related to the measurement-induced transition. But let me change the question. Is it reasonable to consider like the noise happens with a probability? So it doesn't happen always like your setting. I think in the setting you consider the noise will always happen after you give them each gate. Is it reasonable and interesting to consider if the noise will happen occasionally, so with a probability instead of it happens always times?
Yeah, okay, that's a very interesting question. And yes, you can have the noise happens not, happen with some probability on each qubit. I mean, you can have the, I mean, I guess I heard a few, like twice talks like on this measurement-induced phase transition, and I think that there the model is that they sample the qubits, the like qubit label like 1, 2, I don't know, like and then apply the reset that qubits. Is it the right model? This right? You are asking
yes,
this.
for example, after this step, you measure with a probability, yes, in some sense. Yeah.
You don't reset all the qubits. Yeah, I mean, that's within our model because, I mean, also convex combination of noise channel is a noise channel. And I mean, a replacer channel, if you have, replacer channel, it's something that keeps you, I mean, in zero, gives you, takes a state, gives you 0. This is a channel. And a probabilistic reset is just a convex combination between the initial state and this 0 state. So this is a valid quantum channel, and our noise, I mean, our assumption are for any noise. So, I mean, that's within our model, yes. In particular, probabilistic reset is really really a convex combination noise channel. So, I mean, it's within our framework. Good question. So you can think here also that with some probability you apply a noise on each qubit. Yes.
I see. Yeah, thanks.
Oh. I don't know really if in the measurement-induced phase transition, you, with some probability, each qubit is independent. I don't know if it's only one qubit that is resetted per layer, or also multiple qubits can be resetted. I mean,
it's something like after each layer, you measure each qubit with a probability. So independently. Yeah, so it is possible to measure multiple qubits at the same time.
So sorry, I didn't hear very well. With some probability, I mean, you pick randomly one qubit and you reset with some probability you reset this, or with each qubit you toss a coin that you can reset it for each qubit independently. I mean, the reset of a qubit influences the reset.
They consider each qubit independently. Yes, and so for each qubit, for example, it has 0.2 probability, and to do the measurement, and it occurs the reset. Yes.
Okay. Yeah. Okay. Yes, I think. I think that many. I think these things of measurement-induced, like measurement-induced phase transition framework. Yeah, I mean, can be studied also within our framework. But yeah, here the noise channel is, I think, is consistent with. Could be, I mean, taken consistent with our assumption. I mean, of course, I mean, one needs to really take this particular noise channel. We have in our paper the parameters. If you take the parameters really like this probabilistic reset, then you have maybe you have something in this model of probabilistic reset. But crucially, this in our work we provide most of our like result for expectation value, Pauli expectation value. For purity or for entanglement, we don't have much.
I see. Okay. Yeah, cool. So I guess there will be no question from the audience. And thanks again, Antonio, for the very detailed and answering all our questions. Yeah, we know what our questions just by flying around, and thanks for address them in a clear way. And yeah, see you guys next time. Yeah, bye-bye.
Okay, thank you so much. And yeah, happy to see some of you at TQC. Okay.
Yep.
Bye-bye.
Bye. See you.